Good day, everyone. I am Evita Ruth Ramos, and together with Neil Bayer, this is our presentation for Module 14, the Transport Layer. Role of the Transport Layer. The Transport Layer is the core of the Internet model. The application layer programs interact with each other using the services of the Transport Layer. Transport Layer provides services to the application layer and takes services from the network layer. In simpler terms, one of the primary jobs of the transport layer is to divide all the data received from the application layer protocols into equal segments, which can then be mixed together or multiplexed and passed to the next layer for processing. So the role of the transport layer includes ensures end-to-end communication, manages data segmentation and reassembly, provides error detection and correction, and supports flow and congestion control. So the transport layer also has responsibilities. The transport layer plays a crucial role in ensuring smooth communication between devices. It manages multiple connections, allowing different applications to communicate simultaneously. It segments and reassembles data, making sure that messages are delivered in the correct order. It also adds header information to help identify and separate multiple conversations happening on the same network. Additionally, it ensures both reliable and unreliable communication based on the chosen protocol. It establishes and terminates connections, and most importantly, maintains data integrity and flow control to prevent congestion and data loss. Transport Layer Protocols. The Transport Layer Protocols specifies how to transfer messages between hosts. It is also responsible for managing reliability requirements of a conversation. IP does not specify how delivery or transportation of packets takes place. So there are two main types of layer protocols. The first one is the Transmission Control Protocol, or TCP, and the other is the User Datagram Protocol, or the UDP. The right transport layer protocol for the right application. When choosing the right transport layer protocol for an application, TCP is generally preferred for applications requiring reliable order data delivery, like file transfers, emails, and web browsing, while UDP is better suited for applications where timely delivery is crucial over absolute reliability, such as streaming video, voice calls, and online gaming. So there are also key points to consider. For TCP, which is a connection-oriented protocol, it establishes a connection before sending data, ensuring data arrives in the correct order and is error-checked. It is ideal for applications where data integrity is critical and some delay is acceptable. Some examples of these are HTTP web browsing, FTP file transfer, and SMTP, which is email. And for the UDP, which is a connectionless protocol, does not establish a connection beforehand, sending data packets individually. Faster transmission with less overhead, but no guarantee of delivery or order. Suitable for applications where fast response is crucial even if a few packets are lost. So some examples for this are streaming videos and voice over IP and online gaming.
There are two main protocols in the transport layer of the OSI model, the Transmission Control Protocol and the User Datagram Protocol. I will first discuss the Transmission Control Protocol. The features of TCP include session establishment, reliability of transmission, ensures that data is delivered the same order it was transmitted, uses full duplex communication, and supports flow control. Transmission Control Protocol establishes a connection with the destination device before sending data. This feature utilizes the three-way handshake to establish a secure session. I will explain more about the three-way handshake at the later part of this presentation. It ensures that the destination receives the data sent by the source. It is possible for data to be corrupted or lost during transmission. The destination sends an acknowledgement control bit once a segment reaches the destination. This way, the lost or corrupted data can be retransmitted by the sender. Since data is divided into multiple parts and sent using multiple routes, it can reach the destination in a different order than it was originally transmitted. TCP employs sequence numbers to keep track of the original order of the data when it was transmitted. This way, the server can request the client to retransmit the data when some of the data has been lost on its way to the server. TCP utilizes a full duplex communication. This implies that the server and client can transmit and receive data simultaneously. It can manage network traffic by employing congestion control. When the rate at which data is being transmitted is too high for the server to accommodate, the client will adjust the transmission rate to match the capacity of the server. A TCP header is 20 to 60 bytes long. It is divided into header fields which altogether keep track of the state of the session. The first header is the source port, which identifies the source application by its port number. Next is the destination port, which identifies its destination application port number. The sequence number keeps track of the original order of the data being sent. The acknowledgement number tracks which packets have been received by the server. The data offset header is responsible for expressing the size of the TCP header. It is expressed in 32-bit words. The reserved data header field is a field that is reserved for future use and is always set to 0. The control flag header field determines the state of the session between the client and the server. The checksum header field is the error detection portion of the header, and the urgent pointer determines the least urgent or the last part of the segment. TCP is used in applications where it is essential that the packets are sent in correct order and with no missing bits. These applications include web browsing, emails, SSH, FTP, Telnet, and more. User Datagram Protocol is a protocol of the transport layer which prioritizes sending a large amount of data in a short period of time. As a result, UDP does not have the reliability of TCP and it cannot employ congestion control. Additionally, it does not need to establish a session with the server before sending data. The User Datagram Protocol header is only 8 bytes long. It has 4 headers: the source, which identifies the source port number; the destination, which identifies the destination port number; the length, which identifies the header length; and the checksum, which is used in error correction bits. UDP is used in applications where speed is a priority instead of reliability. It is appropriate in applications which require real-time data. These include video conferencing or voice over IP applications, gaming applications, or any time-sensitive application.
Part numbers. So, multiple separate communications. The transport layer protocols TCP and UDP use port numbers to help handle multiple simultaneous conversations. Each communication between devices involves a source port number, which identifies the originating application on the local host, and a destination port number, which points to the application on the remote host. This allows different applications, such as a web browser and an email client, to communicate at the same time without interference. So now that we have discussed about port numbers, the next thing we need to know is about socket pairs. So when data is sent, the source and the destination ports are embedded within the segment, which is then encapsulated in an IP packet. The combination of an IP address and a port number is called a socket. For example, 192.168.1.10 and 443 represents a connection to a secure web server. The IP address is the 192.168.1.10 and the 443 is the port number. So sockets help distinguish multiple processes on a client and allow multiple connections to a server to be uniquely identified. This ensures that the correct data is delivered to the appropriate application. So of course, now that we know that there are ports that are used, we will also need to know the port number groups. So port numbers are categorized into three main groups. So well-known ports are 0 to 1023, reserved for common services like HTTP port 80, HTTPS port 443, and FTP port 21, and registered ports 1024 to 49151 is assigned by IANA for specific applications. For example, Cisco uses 1812 for radius authentication. Private dynamic ports for 49,152 to 65,535. These are ephemeral ports assigned dynamically when a client initiates a connection. And here are some other examples of well-known ports used by various network services. So port 20 and 21, TCP, used for file transfer protocol. Port 22, TCP, SSH or Secure Shell, TCP, SMTP for email sending, which is port 25, port 53, TCP or UDP for DNS or domain name system, port 80, TCP, HTTP for web browsing, and port 443, which is used for HTTPS or secure web browsing. So these predefined ports allow devices to communicate efficiently and securely over a network. So when using ports, we also need to monitor these ports if it's working or it has been established. And this is where the netstat command comes in. So monitoring network connections is crucial for security and troubleshooting. The netstat commands helps identify active connections and check for potential security threats. For example, running netstat, a display all active ports, while netstat B shows which programs are using those connections. Here we can see a sample output where a specific IP address has been established for the port and the others are not. So this helps network administrators detect unauthorized connections and manage traffic efficiently.
Forwarding packets from the client to the server is the main task of the transmission control protocol. It takes an abstract task such as forwarding packets of data and divides it into processes. Every time it establishes a session or connection with a client, it must manage the connection during the transmission period. To do this, TCP makes use of control flags. There are 6 control flags that is being used by TCP. First is the SYN or synchronization. It is used to establish a connection between client and server. It is the first step in the three-way handshake, and this flag set is the first flag set to be sent by the client to the server. Next is ACK or acknowledgement. It serves as a receipt that the destination has received the packet. Next is PSH or push. This instructs the network to send the data immediately, which bypasses the buffer. Next is URG or urgent. This flag indicates that the particular dataset must be prioritized by the server. Next is fin or finish. This flag is sent when the client is requesting to terminate the session with the server. Last is RST or reset. This instantly terminates the connection established, and the three-way handshake is a way for the client to establish a secure connection to the server. The initiating client will first send a signed or synchronized sequence number to the server. This is done to identify whether there are any available ports in the server. The server will then reply with a SYN-ACK sequence number to verify that there are available ports within the server, along with the ACK sequence number to indicate that the first SYN sequence number sent by the client was received by the server. This process is essential in most internet applications since it initializes the connection parameters and establishes a secure connection between the client and the server. Once the client is finished transmitting data to the server, it will send a fin control flag. Once the server receives this, it will send an ACK receipt and a fin control flag. Once the client receives this, it will send an ACK receipt to the server. This process signifies the termination of an established connection between a client and a server.
So, reliability and flow control. TCP ensures reliable communication by guaranteeing that all data arrives in order and without errors. Excuse me. Unlike UDP, TCP resends lost packets and number packets to maintain order. So there are some key points to this, which is sequence numbers ensure order. So TCP assigns sequence numbers to every byte sent. The receiver reorders out of sequence packets. So prevents packet loss and corruptions. Uses acknowledgements or ACKs to confirm data receipt. So how TCP reorders segments? Packets may take different routes, arrive out of order, and TCP reassembles them correctly before delivering them to the application. This ensures that applications receive data exactly as it was sent, without loss or corruption. TCP reliability, sequence numbers and acknowledgements. So TCP relies on sequence and acknowledgement numbers to track and confirm data delivery between the host. This sequence number represents the first byte of the transmitted segment, while the acknowledgement number tells the sender what the receiver expects next. So, how sequence numbers and acknowledgements work together? The sender transmits a segment with an SEQ or sequence number. The receiver replies with an acknowledgement number, confirming receipt and indicating the next expected byte. For Wireshark and TCP analysis, by default, tools like Wireshark show relative sequence and acknowledgement numbers for easier tracking. TCP handshake and acknowledgement flow. So sequence and acknowledgement numbers are crucial during session initiation, data transfers, and termination. This mechanism ensures that data is delivered accurately even if segments arrive out of order. So for data loss and retransmissions, even in well-optimized networks, data loss can occur. And TCP handles this using retransmission techniques. So, how TCP detects data loss? The receiver does not acknowledge missing segments. The sender detects missing acknowledgement and retransmits. So, for expectation acknowledgement, the receiver acknowledges the last successfully received byte. Before enhancement, TCP would retransmit all unacknowledged segments. For selective acknowledgement or SAC, modern TCP implementation use SAC to acknowledge received data selectively instead of resending all missing segments. TCP only resends specific lost segments, reduces network congestions, and duplicate packets. So with SAC, TCP minimizes unnecessary retransmissions and optimizes efficiency. For the window size and acknowledgements, the sender sends the data in bytes along with the sequence number, and when the receiver receives the data, it acknowledges the sender by sending acknowledgement bytes that it has received the data. The acknowledgement number defines the next expected byte, and the sequence number is used to reassemble the data on the receiver side. So the window size is the field in the TCP segment which must be set before the acknowledgement can be received. Devices can also achieve larger window sizes for larger communication by scaling up the window size. When the receiver receives the TCP segment, it sends an acknowledgement to the sender, which frees its buffer. So here we can see a diagram explaining the use of the window size, sequence number, and acknowledgement number in the TCP segment. As is shown in figure, PC1 has to send the data. The size of the data is 100 bytes, which is the size of the window. Nowadays, the window size is usually 64 MB or larger. The data contains a sequence number which uniquely defines the segment. PC2 is sending an acknowledgement that I have now received 100 bytes. I want bytes starting with 101. When the sender receives the acknowledgement, it sets the bytes starting with 101 as the sequence number, 101, and the acknowledgement number as the last sequence number plus 1. So TCP flow control uses maximum segment size or MSS to define how much data can be sent in a single segment without fragmentation. So MSS calculation, the MSS is typically 1460 bytes for IPv4 networks. It is calculated as MTU, 1500 bytes, minus IP header, 20 bytes, minus TCP header 20 bytes is equals to 1460 bytes. So why is MSS important? It ensures packets are not fragmented, it reduces transmission delays and overhead. By optimizing MSS, TCP maintains efficient data transmissions while avoiding unnecessary fragmentation. TCP flow control congestion avoidance. So TCP prevents network congestions through several key mechanisms. So first, why do congestion occurs? So when too many packets are sent, routers may drop them, causing retransmissions and delay. So congestion control mechanism. Slow start. TCP initially sends small amounts of data and increases transmission rate gradually. Congestion avoidance. If network congestion is detected, TCP reduces its data transmission rate. Congestion window limits the number of unacknowledged segments a sender can send. By dynamically adjusting the data transmission rate, TCP prevents congestion and improves network performance.
As opposed to TCP, User Datagram Protocol does not need to establish a connection with the server. This means that the three-way handshake and the termination process is unnecessary in UDP unlike in TCP. Due to its nature, this eliminates the need for UDP to use control flags which cuts the length of its header. It also does not need to track packets according to their original order and allows for some data loss. What happens is that the client bombards the server with packets during the communication process. This results in a faster transmission of data but is prone to errors and duplications of packet.